What we have here is the introduction to the next unit. We're starting chapter 11, and this is technically 11-1. We're talking about something called Pay It Forward. There's a movie around 2000, the year 2000, with this kid in it. I don't know what his name is. You may recognize his face, but it's about a 12-year-old boy who gets a challenge from his social studies teacher. And if you'd like to see a clip of this, here's a clip of this movie which showing what's going on here. But in a nutshell, what happens is he basically says that him, right here, this is he by himself, would go out and perform a good task or good deed to 3 people. So we have him here all by himself, total of 1 person, going out into the world and doing a good deed for 3 other people. So now we have 3 total people here, and in turn they would each help 3 people as well, and so now we have 9 people here. And what we're doing is we are creating a table of values here. We're starting with 1 person, and then after 1 stage of the development, helping 3 people, we would have 3 people that have been helped, and then each one of them in turn would do 3 people, so we would have a total of 9 people here. So again, if you'd like to see this video, here it is. It kind of walks you through it a little bit. Read through this to understand what's going on. On this worksheet, which goes with it, I'd like for you to first, with your table, read through and pick which type of graph, this first graph, which initially starts to increase and then flattens out over time, this second graph, which is a straight line, and this third graph, which curves going up. Which graph do you think is going to be an example of what we just showed right there? And then once you do that with your table, what do you think after 10 stages, for example, this would be the first stage and this would be the second stage, how many people do you guess, don't use your calculator, just take a random guess, after 10 stages and write that answer here on number 2. Now what we're going to do is go into number 3, and this is really where you need to start paying attention, because this is absolutely where we are going to start creating our exponential model. So we know at stage 0, which is when we're starting, the little boy is all by himself, and he's going to be the beginning. This is where we start doing our good deeds. After the first stage, he had 3 people that he had done good deeds for. Each one of them, in turn, did 3 more people, and so after the second stage, we had 9, and then if each one of those 9 people do 3 more people, we would have 27. Complete the rest of your table exactly as so, and it kind of should be obvious at this point that what we have here is a situation where every single stage goes up by a multiple of 3. So 1 times 3, and then 3. That times 3 was 9, and then times 3 more is 27, and this is where we are after the 3rd stage. So the 4th stage would give us 81. The 5th stage, 243. The 6th stage, 729. The 7th stage, 2,187, and you can see this just continues to get bigger and bigger and bigger as time goes on. The next stage would be 6,561, and then 19,683 people would be touched if we just continue doing this. So let's scroll back up, and I'm going to start copying these numbers down. After 27, there's 27 there. Then we have 81. So I'm going to write an 81. Then we have 243. Then we have 729. Then we have 2,187. Then we have 6,561. And finally, in our table at least, 19,683, all starting from 1. Fairly quickly we see this exact value here. So how did the number of good deeds at each stage, here are our stages up here, grow? Well, it grows by a factor of 3. The reason it grows by a factor of 3 is we're multiplying by 3, by 3, by 3, by 3. Each one of these are times 3 as we go through this system. And this is now what we call exponential growth, because an exponent is when you multiply by the same number over and over and over again. So what we're going to do is we're going to sketch this data, and it's not going to have to be perfect, but at 0 we'll start at 1, so maybe here's 0, comma 1, and then at 1 we'll jump up to 3, and then at 2 right here we're going to jump to 9, so maybe 9's up here, and then at 3 we get way up tall up at 27. As you see, what we're eventually going to do is just run out of space. We can't even graph very many. And just so we understand what's going on in our problem, we can't go beyond 0. Because at stage 0 we can't have a stage -1. So we're only really caring about this. But in reality, the exponential graphs, you should know this, all exponential graphs, and we'll talk about this in a little bit, will look something to this effect. Okay? And on this, we're going to say what the domain of this function is. And the domain here would start at 0. And domain, remember, is all our x values. We're going to start at 0, and then we're going to keep going forever and ever and ever and ever and ever. In theory, we would, and we're going to write this in interval notation. So 0 is where it starts, infinity is where it ends. I'm going to include 0, so I better put a bracket here. And then it does not touch infinity, so I can't ever be infinity, so a parentheses there. The range, remember, is all the y values, and if you look here, I'm starting with a y value of 1, and I'm also increasing forever. So this will be 1 to infinity. And again, we're going to put a bracket on the 1 because I can touch 1. It's starting with that little boy all by himself in the situation. On which interval is the function increasing? So on the next part, to increase means to go up. Remember, you always read a graph from left to right. So as we read this, we're on the left and we are increasing, going up. So really what's happening is it's always going up. The graph is always going up. So it's always going up. Well, what interval? That means what x values makes the graph go up. What x values are from 0 to forever. All of the x values are going up. So we're going to say 0 to infinity. And these are all the x values. So if the function's always increasing, could it ever be decreasing? And obviously the answer is none. It's never decreasing whatsoever. It's not going down. Okay? Asymptotes, on this one there are no asymptotes because we're starting exactly here, but if you look on the generic exponential graph, there is an asymptote, and that asymptote is right across. Remember asymptotes from a long time ago? Those are lines where you kind of get close to, but you never really touch, and this, by the way, would be the line y equals 0. So keep in mind later on when we do some more graphs of exponentials that you are going to have an asymptote typically at y equals 0. For us, we don't have it because this is a real application, and we don't have to worry about finding anything less than stage 0. All right, does this shape match one of these shapes? Hopefully you picked stage 3 here, or option 3. And this is called an exponential graph. Exponential graphs are very important because they increase very rapidly. And if you want rapid growth, for example, population growth is an exponential model. More people are born than die, and what happens, obviously, each generation, what happens is we get more and more people on the planet. So that would be an example of exponential growth. This one's very important. We're going to write now a rule. Our rule is going to be n's compared to x's. Think of this as y. You could call it y if you'd like to. Same idea. But the general model for exponential graphs always look like this. This is the parent for exponential, and then we're going to make it specific here. The parent is always y equals a times b to the x power. Okay? A is always your starting amount. So look up here in our table. What did we start at? And I don't want the x number. I want the number of deeds that we started. Well, we started with just one boy by himself. So that will be our a number. So our equation here is going to be 1 to start. B is what's called our base, or what we are continually multiplying by. Sometimes they call it the ratio. Okay, so B here would be our ratio. Whereas A here is what's our starting value, or they call this the initial value. And B is our ratio. So as you look up here, we start at 1, and then the next answer is 3, and then 9, and then 27, and 81. Well, B says, how do I get to 3? And how do I get to 9? And how do I get to 21? So B has to be the number that we're multiplying by. And here we're multiplying by 3, by 3, by 3, by 3 each time. So that's going to be now our B number. And then we always raise it to a power of x. And so now our equation is, since we're going to do n instead of y, we'll say n of x equals this equation. And I want you to graph that real quick. Go to your graphing calculator and type in 1 times 3 to the x power and see if it kind of matches our table here. I'll give you a second to do that. You might want to pause the video here. Okay, you should have had enough time. Let's go ahead and look what this looks like. 1 times 3 raised to the x power. And I'm going to show you my table first to show you that hopefully we get the same values. So if I start my table off at 0, notice I have one person. That's what we started with. At the first stage, then I get 3. The second stage, I get 9. And the third stage, you get 27. All of these are the exact same answers as we have in our table. And if I graph this, let's see, I'm going to go zoom 6, my standard window. If I graph this, you can kind of see what's happening. We have a horizontal line right at the x-axis. That's our y equals 0 right here, asymptote. So it's never going to go below. Notice we never get negative answers down here. Oops. But then it starts to increase very, very, very rapidly, going up, which is kind of like what we're seeing right here as well. And notice it also mimics graph number 3. Okay, so this is an exponential graph. You need to know this formula. Y equals a times b to the x power. A is your initial amount or starting amount. B is the ratio that you're using, and then you always raise it to a power of x. Very simple function. Okay. All right, either continuing this pattern or using your equation, how many stages of the pay it forward process will be needed for a total of at least 25,000 good deeds to be done? Well, we've already graphed this, so let's just use our graph. So I'm going to go to my table, and I want to find an answer way over here when we want 25,000 people. And if you remember up here, at the 9th stage, we're really close to 25,000 anyway. We're at 19,000. That was way down right here. So the 9th stage gives us 19,000, and the 10th stage immediately jumps way up here to 59,000. We're quickly improving the next. So really, how many stages do we need for at least 25? Well, it's not 9 because that's 19,000. That's not at least 25. So we need 10 stages because at the 10th stage, we will have 59,049 people, which is certainly at least 25,000. Only 10 stages. All right, flip it over on the back, and now we're going to go backwards. Is it possible to pay it backwards? Well, that just kind of means if you're going backwards instead of forwards, we're now talking about, instead of growth, we're going to be talking about this thing called decay. Okay, decay means to go down. And just so you know, a decay function, if growth goes up, decay is going to obviously come down. And again, just like before, you're going to have an asymptote right at this x-axis, which is the line y equals 0, only now we're going down instead of up. So read through this. Bill Gates, who is a known philanthropist. I'm not sure if you know who Bill Gates is. I hope you do. He's the one who created all of this computer technology, or at least, I don't know if he created it as much as just made it popular with Windows. But he has amassed a fortune of roughly $84 billion, and he's what's called a philanthropist. He gives away lots and lots of money every year to charity. So let's suppose every year he gives away half of his money to charity. So what's going to happen to his fortune? Obviously, if he's giving it away, he's going to be losing some of his money. And he's going to be losing exactly half every year. And this still follows the exponential model, but now instead of multiplying by 3, we're going to be multiplying by 1/2 of his money. So we have $84 billion at year 0, and we're starting this. And after the first year, he gives away half of his money, which means he has $42 billion left. Then he's going to give away half again, so we're again going to times it by 1/2, and now we get $21 billion. Keep filling out this table by multiplying by 1/2 each time, multiply by 1/2, and you will now have a situation where we have found exponential decay. So fill in the remainder of your table now. Alright, so if I'm at $21 billion, I'm going to multiply it by 1/2, and I now get 10.5. So let's put that in the stage 3. We're at 10.5 now. I'm going to multiply that by 1/2, and I get 5.25. And remember, we're in billions. That's still a lot of money, $5 billion. I wish I had even a little bit of that. Times 0.5. Now we're at $2.625 billion. And keep in mind, based off scientific notation, if you have $2.625 billion, That means you have $2,625,000,000. That's still quite a significant amount. All right, times 0.5 again. Now we're at $1.3125 billion. So in other words, $1,312,500,000. And then one more in our table, and we get 0.65625. And this is important because we have no more billions left. But we still have 600 million because it's the next decimal place. And even though we're in decimals, we're in billions. So before billions means we're talking about millions. So 656 is million, 656 million. Then we're at 100,000, 10,000. So we still have $250,000 after that. So what's happening every single year? Well, we are losing half of the money that we had before. So what will this sketch look like? Well, it's going to kind of look like what we had up here. We're going to have at 0, so x is 0, we're going to be way up here at 84, and we're just going to sketch it, so that's going to be 0, 84. And from here, we are going to be going down, and eventually we are going to be flat. We're going to have no money at some point in time. At 1, right here, we'll be about halfway, so that might be 142. At 2 over here, we'll be half of that, so that might be 221. At 3 over here will be half of 21, 10.5, and it just keeps going this direction. All right, fill in these numbers now. The domain. The domain, remember, is all your x's. Well, what did I start with in my x's? I started at 0, and I'm going to forever go on. Even though I'm getting smaller and smaller and smaller, I still have something left. So we're going to say my domain is from 0 to infinity. My range are all my answers, so I started this answer at 84. These are my y values. And I'm not actually going to get to infinity this time because notice I'm getting smaller and smaller. So now I can never get less than 0 starting at 84. And you can't actually touch 0 because theoretically you can take half of 1 to get a half and half of that to get a quarter and half of that. And this just keeps going forever. So you'll always get half of something. On what interval is it increasing? Well, if you look at the graph, remember we read from left to right, we're never increasing. Everything this time is decreasing, so that means always we're decreasing. So we're going to be decreasing from 0 to infinity. And by the way, there should never be a bracket on your intervals because that's just where you start and end. And asymptotes, this graph has no asymptotes, but in reality, we are going to have an asymptote at y equals 0 for a generic exponential decay model. But for this one, it's specific, so we do not have an asymptote here. For this model. Actually, I take that back. We do have one right here because we are getting smaller. So we actually do have an asymptote at y equals 0. I apologize. We do. For growth, we do not. We will never actually cross this x-axis because we're always going to be taking half. And write a rule residing. Well, this rule will be the exact same as before. So a times b to the x power. So this case, remember, a is what you start with. So look in your table. What number do we start at? Well, we start at 84. B is what we multiply by. Each time it's called the ratio. So we're multiplying by a half, by a half, by a half, by a half. So we will multiply by 1/2, and then we raise that to the x power because this is exponential. It just happens to be decay because we are less than 1 when we multiply. And this becomes our equation based off of m. So we're going to say m of x equals 84 times 1/2 to the x power. This is still exponential equations, only now we are decaying rather than growing. Okay? Last question. Either continuing this pattern or using your equation above, after how many stages will Bill Gates have a total of $10 million left? So think about it. 10 million is 1/100th of a billion. So if I had $1 billion, there's $1 billion. My 10 millionth number is right here. This becomes 10 million. Well, how do I get there? That basically means here's my decimal, I'm going to move it 2 decimal places, 0, 1. I want a 1 right there. All right, so I'm going to move it over to the 100th, sorry. This is the 10th, this is the 100th place. So I'm going to look at my calculator for that value. I'm going to come over here and I'm going to type in my equation because that's going to help me out. Here's my equation. 84 times 0.5 raised to the x power. Now I'm going to go to my table. I started at 84 in my table, which is perfect because that matches my graph over here. And then I had 42, there's 42, and then I had 21, and then I had 10.5, and I want to find $10 million, which is 0.01. Well, right here at the 13th stage, I have 0.01. That is $10 million. So it looks like after 13 stages, and each stage is a year, this would be after 13 years, we should have approximately $10 million according to our stage, or somewhere right around the 13th year. I guess technically it would be between the 12th and the 13th. The 12th I have 20 million, and then the 10th I have, or 13th I have 10 million, so it's going to be somewhere between there, but that's good enough for answering this question and being able to figure it out. So that is an explanation of exponential growth and decay. Remember that equation, y equals a times b to the x power. Once you have this finished, go ahead and turn it back into the sub, pick up your homework page, and see if you can figure out those answers. By the way, on the homework page, if I have this situation and you did not know how to get what I multiplied by, you could easily say, well, what's the opposite of multiplying? And that answer is division. So I can take the second answer, 42, divide it by the first answer, 84, and I get 0.5. That is our b value in the equation. So take the second one, divide it by the first. On the front page, you can do the same idea. You'll need this for your homework. Let's say I take the second answer, 3, and divide it by the first answer, 1. 3 divided by 1, that means I'm multiplying everything by 3. And this works for all values. If I divide 9 by 3, I still get 3. 27 by 9, I still get 3. So use that when you're doing the homework page tonight to find your b value. Good luck.